see whether the
Recording in
share.
progress.
Yeah, recorded. If you have a bit more time, we can sit a bit longer till 4 so that I kind of make up for the time. Depends.
That's okay. I just have a meeting at 5.
At
But
5, then it's fine. Then we can sit a bit longer that I make up for the time. So let's go. Do you see my screen?
yes.
So the question was, why, when you have a machine, when you have, let's say, two machines, and you have to, and you basically share, you decide that it's probability half. You have, let's say, machines. So you have a task Wi, which was weight 1, and machine with S1 is equal to S2 is equal to 1. So the speed of the machine is also 1. And you decide that this probability half, task 1 goes to machine 1, and this probability half, task 1 goes to machine 2. Why? Then I consider the utility of the task, the cost basically, not the utility. Yeah, it's a cost. Why? They're considered to be is cost 1 equal to half of probability half. You have a task of size 1 or the machine of speed 1 plus probability half, the same, just the machine is a different machine, and the average is just half of average of 1 and 1. That's 1. Why is it 1 rather than the maximum between basically the halves? Why is it not the maximum? I can tell that half of the task basically runs on one machine, the other half runs on another machine. So it can be like half divided by 1 plus half divided by 1, not plus, excuse me, the maximum between them. Why is it not the maximum, which is of course half? So that was your question pretty much, right?
Yes.
And the answer is actually simple. In general, what does it mean? I was also confused a little bit, because from one point of view, I see that we just have this normal mixed profile. From the other point of view, since this concrete case looks at this sharing of time, this scheduling of tasks, why isn't that the case? So the answer is actually simple. The mixed profiles don't model this actual sharing of tasks in that sense.
Yeah. It's just a probability of picking a machine rather than dividing the tasks.
Yes, it can be seen as dividing the tasks, but only if the eventual cost will be defined according to these context combination rules, and not according to something else such as the maximum.
Mm-hmm.
So basically, the answer is, and I agree it's a bit confusing. At least it was a bit. Suddenly, you are used to work with something, and suddenly you have this. Oh, why isn't that? I have this feelings of suddenly the kind of floor is basically shaking from below my feet. I know that, and I don't know whether it's only I have this feeling or not. But anyway, the answer is, so the mixing models again a convex combination, so a combination of non-negative factors, sum of which is equal to 1. Convex combinations for y combination which can be interpreted as probabilities. I don't have any space in my. It's not so, I don't like the ugliness of what I write myself. That's why. As probabilities. Load sharing or anything else which fits the formula. Maximum doesn't fit the formula. That's the idea. So it's basically I just take the pure strategy, and then the maximum is the thing that the agent experiences, or I can take any mixing of the strategy, but it is going to be a mixing on those pure strategy. It's going to be a mixing according to this rule of mixing. That's simply what happens. By the way, when we're talking about in general, when we have this strategy, there is a chance that mixing in general. So when I take half of some strategy in any game, forget this game, there is a chance that it's going to be non-linear. It's not going to influence the situation in a linear manner. That is fine, but then I have to just tell that it's not a mixed extension. It has to be modeled as another game. And mixed extension models, anything, for example, probabilities, anything which fits the formula. It doesn't have to be probability, simply that they fit the formula. And they're probably the most famous interpretation. So I hope is it more clear now?
Yes.
Okay, great. So let's move then to question 1. And so we needed to finish a question which I was trying to prove. Actually, I was using the proof I had thought about myself, and not surprisingly, sometimes I find mistakes of my own. Again, even in the book, I find mistakes, not only typos. So maybe it's my mistake. Maybe I'm confused. But definitely, when I just think of something that it's a chance of making a mistake, so it's fine. But now we need just to solve that, of course, correctly. So let's move to the exercises. So there wasn't. Okay. Now, so the question was proof that a fully mixed Nash equilibrium on an identical machine. It can be only this fully mixed Nash equilibrium. I remind that fully mixed means that everyone's support is all the strategies. Everyone has a full support. In other words, every player gives a positive, strictly positive probability to each strategy. And the question is, so which full mixed Nash equilibria exist? So we know that the machines are identical, then at least the fully mixed Nash equilibria of just given the same probability 1 over the number of machines to every machine exists. And we wanted to prove that it's the only one. That's something which the book tells, and I tried to prove it, and I got confused at some point. I mean, I didn't get confused even. I basically was following my reason, which I had thought about some time ago, and then I found that it doesn't work. And now I thought of another reason. So let me let me try. It's not even by induction. Let me try do it by another reason. So prove that for any number of machines, players are tasked, at least 2, there exists exactly one fully mixed Nash equilibrium on identical machines. And the question is, what is it? So what is it we have told about? What is it? We can just write it down. Problem 1. So the profile EiG 1 over M for any I and for any J is fully mixed, and it's also a mixed Nash equilibrium, not mixed Nash equilibrium. Now we now prove that it's that it's unique for any number of players, at least 2. Now, it's, by the way, not the case, a remark, for a remark. So for a single player, it's of course a degenerate game, but still, what happens? Sometimes it's instant. So what happens for a single player? That's not the case. Can you tell me why? Why is it not unique for a single player?
Any mixing would be a best of response, right? Because all the machines are essentially free,
Exactly.
assuming they're identical.
Assuming what?
They're identical, and it's in the question, yes.
Exactly. Okay, mixing, we can just look at this as a particular case of a game, of a mixing. So any pure strategy has the same value, and therefore any mixing is fine. For any pure strategy, and the reason is identical machines, has the same value, the same utility, whatever we call cost. Cost here has the same cost, and thus any mixing, any mixed strategy is optimum. It's the best response, but it's one player, so it's also an equilibrium. It's the best response, and therefore it's a mixed Nash equilibrium because there is only one player. That was just a remark. Now, what happens for n at least 2? That's actually something which is interesting. So for any player I, if we look at what happens besides that player, what happens besides that player is that the rest have to have the same, have to give that player the same law, so that she will want to admit. Hello, we are solving question 1, which I started at the previous lesson, but then I found a mistake in my proof. So you have not missed much because there was a technical problem. Yet another student. Hello. So going back, they are solving question 1. So going back to the solution. For any player, what happens is that the fact that the player, for any player, the fact that the player has a full support means that all the strategies have the same, even in particular the best value for that player. So what it means is that if I look at the expected load of each machine minus the expected load of that player, and so if I look at the expected load of the others, that has to be the same for every so expected load the other task created by each machine. So for each machine, if I look at the other task, j, which are not equal to I, the expected load which they create on machine, let's call it P in Q, is the same. Otherwise, the player would not have full support because PI has full support, has the full support. So there is a reason I want to mix all the strategies. It means that all of them have to have the same value. Good. So, by the way, formally, I think that we need to tell the other students, is it okay if we record this? Please let us know if it's not okay, because formally, I think we need the agreement of everyone. So please let us know if someone does not like. Let us know in the chat or by words. Okay. Anyway, let's go back. So PI has full support. Therefore, what the other players create is basically the same. And that happens for every player. What the others do is the same. Now, what it basically means is that all the variations that player can have in investing in various machines, and all the probability variations, they have to be exactly because of this player only, because the rest just create the same thing for every two machines. Now, therefore, the total sum of the player also has the same variations as this player. So if there is any variation, so Pi going to machine, let's go P and Q, going to machine P, P and Q can be confusing. Let's call it rho and Q, because P is already probability. So Pi going to machine rho minus Pi going to machine Q, this difference in probabilities is exactly the same as the difference in probabilities among the total load of all the players, J, because the others don't have any difference. That's what we have here. Is that clear? I realize it kind of may be confusing. So is that clear?
Could you please repeat again? I got
Yes,
lost
sure.
here.
By the way, again, since I just thought of a proof at some point, it's not like something that has been checked by many people. There is no guarantee that it's true. So don't be afraid of asking. Maybe there is a mistake. Again, for any player, it has a full support. It means that the other players create the same load on all the machines. So if I look at the expectations of the other players, J's which are not equal to I, for any row and Q, this is exactly the same. For any row and Q, which are machines, 1 to M. Do you understand that part?
Yes.
Therefore, the intuition tells us we are going to kind of prove that there is no variation between, no variation is a mathematical, that's what I mean. There is no difference between what a player, what is the probability the player, any player basically, gives machine 1 and machine 2, gives machine rho and machine Q. There is no, that's what we need to prove. Now what we say is that the other machines, the other players, excuse me, in total, don't have any difference. That player may have some difference. Now that has therefore to be exactly the same difference as the difference of all the machines, because the others don't have anything. So the difference between what player I can give to machine Q and what player I gives to machine rho is exactly the same as the difference in all what everyone together gives to machine Q and gives to machine rho. Let me just write the illustrations. I mean, so for example, I have rho and Q, two machines. Excuse me. All the players beside player I have exactly the same picture for those two machines. And of course, I have drawn it very clearly, but now it's going to be better. So all the players have exactly the same picture for those two machines. Maybe player I actually has something larger for machine rho than for machine Q. Maybe. But then, since the rest have the same, and maybe player I is the only player who may have some difference, then the total load also is exactly, if it's different between rho and Q, the difference is exactly because of player I. Do you understand it now?
Yes.
Okay, don't worry if you don't, let me know every time, because I realize it can be confusing. It's actually good that I explain it several times. Good. Now that thing holds for any player I. That's the cool thing. It holds for any player I. Any I 1 till n. Since any player, if there is something, the difference between the total load on I on rho and Q, that's exactly what player I has. Now that's true for player 1, for player 2, for any player. Therefore, it cannot be that this difference is different from 0, because then the total difference would be different from 0 for let's say all the other machines, because for everyone, but it's not. So since it's for any player I, the conclusion is that basically it's equal to 0. Is that fine?
Yes.
So this picture is for any player I. That's equal to 0. And of course, then that's basically what we proved. So for any player I, for any two machines, there is no difference between what player I gives to rho, and there is no difference between what player I gives to Q. So for any player I 1 till n, and for any rho Q in the set of machines 1 till m, the probability that play I gives to rho is equal to the probability that play I gives to q. And that's what we need to prove. I hope it's clear. Fine?
Yes.
Good. Please notice that in the previous proof, which I tried to pull off, it was problematic because then the induction didn't work at some point. Maybe I could have somehow circumvented it. But what I want to say is that I didn't actually use that fact that it was true for any player. I just took some player and I said it's true and what I have here. But I didn't use the fact that it's true for any player, and therefore maybe it was hard for me to kind of circumvent this problem. The induction basically stalled, as you remember. Good.
Yeah.
So we are done with this question. Now there is another question which we'll probably not do now. We'll probably pull it. After I had written that problem, I noticed actually another question. I was surprised. The book actually tells something different. Let's look at exercise 20.5 on page 542 in the book. Okay. I don't have let me now open the book. The book says something which is stronger. They actually have a nice exercise, but their proofs, I guess, more technical than ours. Okay, we need to make a break. But okay, let's finish it and then take a break. F theory. So 542. That's what the proof is. So what the book basically tells us, exercise 20.5. Do you see it?
Yes.
They want to show that there exists at most one fully mixed Nash equilibrium for any instance of load balancing game. For the case of identical machines, we know that's the case. There exists exactly one. We know which one, and we showed it's the only one. Now, for any instance, there exists at most one. So if we use that way of proof, which we now read how to do it, the hint, then we would be able to prove what we also have in another way. Because basically, we know that there exists something, we show that these uniform probabilities, they are in equilibrium, and we'll be able to claim that it has to be the only one. Now, what is their way to prove it? There is at most one fully mixed Nash equilibrium. I remind you, fully mixed means it has a full support. So every strategy has a non-negative, a non-zero way. So the hint is, we describe the conditions and systems of linear equations, show it has a unique solution. I guess it's something with the determinant being non-zero, a square matrix, something like that. And if that's what we do, then, of course, if all the values of the variable indeed are positive, then it's going to be actually a solution, and otherwise there is no Nash equilibrium, no fully mixed Nash equilibrium. There is no solution where all those values are strictly positive. So that's the way of proof. So probably it's more technical than what we do, and we need to think how to express that and all that, and to see that we can prove that the determinant is non-zero. So it's probably a bit more technical, but then we can prove this stronger statement. But let's not do it now. it does not seem to be a wise use of our time. And we are going to actually do something nice, really nice, after the break, which is the tightness of this bound we saw at class. So let's make a break as usual, 10 minutes. I see you in 10 minutes.
Okay.
Recording in progress.
By the way, the student who was not here just want to tell that we had a technical problem, so we might sit a bit longer. If you do have a problem with that, let us know, because I just wanted to kind of give back the time which we lost because of a technical problem in my tablet. So going back to the exercise now. So we need to solve the product. Remember that we have this bound for exercise 20.2. Let's go to the exercise 20.2. So we set this bound that the cost of any equilibrium, pure equilibrium on identical machines, is at most 2 minus 2 divided by n plus 1 times the optimum. We had this bound on lectures. I remind you, if you don't remember, there is this bound in the book, of course. Now what I want us to show is in this exercise is that actually that can be tapped, so that cannot be generally spoken in proof. For any m, there exists an instance of a load balancing game with m identical machines and 2m tasks. Such that there is a pure equilibrium costing exactly this factor 2 minus 2 divided by n plus 1 times the optimum. And they give us this hint that we need to generalize the example from section 21.2. Let's go back to that section. Let's go back to that section. I remind you about example. But actually we saw it in class. But let me just tell you this quickly, remind you the example that you had two machines and two tasks of weight 1 and two tasks of weight 2. So the optimum, of course, would be just to assign 2 and 1, those two different tasks to one machine, and that two and 1, I mean the sizes, to the other machine. The machines were identical. Then it would be optimum. There was, however, another equilibrium where you assign the two tasks which are larger, which have size 2 each, to one machine, and the two smaller tasks of size 1 each to the other machine. It's still an equilibrium, because if something from these more load machines wants to move, then there is no improvement, because besides that task of size 2, there is another task of size 2 on his machine. And on the other machine, there are just two tasks of size 1 each. So there is also a total of size 2, and the speeds are the same. So there is no reason to move. And then it gave us this thing that we now need to generalize, and we want eventually to get this bound. M plus 1 can be a hint. Do you have any idea how to generalize this? It's not so trivial, but M plus 1 can be a hint. So how can we generalize the example? For M machine, two M tasks, identical machines, such that there are two equilibria. One is optimum, the other one is going to be non-optimum. Actually, what I require is to have just an optimum thing, and well, if the optimum is also an equilibrium, there is always an optimum equilibrium. That's something we know for those games. So have you got any, please think, maybe you have some idea how to do it. You don't have to give immediately the right result, the right example. It's not easy, but it's not hard actually. So let me start writing, and then maybe you give me some idea of yours. So So problem 3. 20.3 on page 542 in the book. Good. So let's try example. So imagine you have M machines. The sizes are not, should not be different. I simply have drawn it like that. The speeds are the same. So imagine you have M machines. Machine 1, machine 2, machine M. You have M plus 2M tasks, twice as many as machines. Which sizes do you suggest the tasks have? And how do you suggest to, well, let's start with the sizes. If you find the sizes, it's going to be quite simple to find the rest. So do you have any suggestions? Well, how can we generalize what we have there? Because the sizes there were 2, 2, 1, 1. And there were 2 machines. So there it was M equals to 2. I thought of 2 options. One is to give the sizes of 1 till M, and the same, so 1, 1, 2, 2, and so on till mm. The other one is to give this 2 to the power of 0, 2 to the power of 1, and so on. 2 to the power of, again, twice 2 to the power of 0, twice 2 to the power of 1, till twice 2 to the power of m minus 1. The first option was the better one. I thought of that second, but it was the better one. So let the tasks be the size is 1, 1. So 2 tasks of size 1 each, 2 tasks of size 2 each, so on, till mm. Do you understand?
Yes.
Okay. What now is the optimum assignment? It's also in equilibrium, but it doesn't matter. What will be assigned those 2m tasks optimally?
Group the extreme tasks together, I guess.
Right. So that we'll have exactly the same value, and the same value is going to be m plus 1. That's why I told you that's a hint. So on machine 1, so first of all, you put task of size 1, 2, and so on to size m. And then you put the, as we said, extreme task of size m minus 1 till size 1. So on this machine, the total weight is m plus 1. The size of the speed of the machine is 1. So these are just machines. The speed of the machine is 1. And then, so optimum is equal to simply m plus 1 divided by 1, and m plus 1. Now, suggest another equilibrium. It doesn't matter if optimum is also an equilibrium, but suggest something else which is an equilibrium now that will matter, which will have a worse make span. Consider also the suggest a pure equilibrium which will have a worse make span. So rearrange those tasks differently. So you remember how that example of a 2 goes. It's not easy actually to generalize because it was only 2. But still think of another equilibrium. We cannot, of course, put mm, so we cannot put like 1, 1, 2, 2, 3, 3, mm. It won't be an equilibrium because then the task from mm would like to move to 1, 1, for example. That's not a generalization which will be an equilibrium. But we can do something else.
What if it's m by 2 and 1?
M by what?
No, that wouldn't work, I guess.
No, what I think that actually it sounds good what you told me.
I said like maybe like 1 and maybe m by 2 is grouped together, but then
Okay, so you suggest to shift
by half.
by half.
Yeah.
By half, then it's aha. Are you sure that you want to shift it by half? So okay, good. Let's shift. So then it's not going to be by 2. It's, m divided by 2, you mean?
Yes.
M with well, let's try it. Maybe you actually find another way to solve it. Nobody tells that my solution is good. I mean, it should be good unless I've made a mistake, but nobody claims that's the only one. Maybe you find another one also fine. So let's see. You suggest basically. So those are the machines. That's right. Like Hebrew from right to left. Machines. So first of all, you have those tasks 1, 2, m. But the second row of the task, so to speak, you suggest putting task so 1 with m by 2, 2 with m by 2 plus 1, right?
Yes.
And the m at some point is going to be m in the middle, and then it's going to go just 1 and so on until you have m by 2 minus 1.
I don't think this is good, right?
Let's see whether it works. It's not what I thought about. Let's see whether it's in equilibrium. The task from... So let's see. Now, the task from m by 2 minus 1, which sits at the rightmost machine, at the machine m. This task, which weighs m by 2 minus 1, it faces besides himself m. Now, if it moves to machine 1, it would face m divided by 2, so it would be better.
Yeah.
It's not an equilibrium.
Yeah.
But so it's not an equilibrium. It's not an equilibrium. But what about another example? What about shifting those things differently? So it does work for me to shift it, but just think about some other shift. It did take some time, so don't worry if it takes you time. I didn't think of that like in a second, but I just of course want to do it quicker than I was thinking about it. But basically, think about another shift which might be an equilibrium. I'll prepare the. So there are those machines 1, 2 till n. So those are machines. So let's assume that those tasks don't change. Well, without for generality, they don't change because the machines are identical. What about the second row of tasks? So what about shifting that a little bit?
Yeah, I had just written that. What if I just shift? I put m minus 1 in the first bin, m minus 2 in the second bin, and so on and so forth.
So you suggest to shift that to the left, so to speak.
Yes.
And of course, and to the left, and then just go like that, right?
Yes.
You need to make it cyclical. So m minus 1, m minus 2, and then it's going to be m, and here it's going to be 1, well, m minus 1. Let's see. So first of all, is that an equilibrium? So who might move? What I think now that the lot, no, that's still not an equilibrium, because then she's okay, no, actually, wait a second, maybe that is an equilibrium. One second, please. Who is the task who wants to deviate the most? The task who faces the heavier.
Professor, I think okay.
Yes, I don't hear you.
Yeah, so for some time, like your voice had completely cut off, so I thought like it was
Okay. My apologies. So from which, well, it's not my fault anyway, but from which point did you not hear me?
You had said this might be, you asked who might want to shift the most.
Yes, we want to make sure it's an equilibrium. How do we check? Let's see which task would like to change. If there is someone who wants to deviate, who would be the first to deviate, so to speak? Who definitely would like to deviate?
Probably the person grouped with M, right?
Right. Actually, so someone who sits here. Now, what that person sees is a task which weighs M. Now, if you deviate, what you're going to see is what you have on that machine till now. But in any other machine, the total weight you have is exactly M. M minus 1 plus 1, M minus 2 plus 2, and so on. It's exactly M. Right?
Yes.
So it is an equilibrium. On each machine, smaller than M, the total load is M. So on each machine smaller than M, the total load is M. Therefore, even a task facing M already, M on machine M, won't deviate, and therefore it means it's an equilibrium. Is it clear?
Yes, because like there is already M there, and you already have an M if you want to shift
Exactly.
the last task. Yeah.
So what's going to be the social, or what is the cost? Its cost
2M.
is 2M exactly, and then the ratio is 2M divided by what was the cost of this?
M plus 1.
M plus 1. Yes. Yes, it was always M plus 1. It was uniform. Here there is some uniformity, and then there is this phi here on machine M. But the optimal is was complete uniformity. 2M divided by M plus 1, and that's simply 2M plus 1. So 2 twice M plus 1 minus 2, 2M, yes, which is equal to 2 minus 2 divided by M plus 1, exactly what we need, right? Yes. So we are done. Any questions?
Uh,
Excuse me, if you told something, I didn't hear that.
I was wondering how the 2m divided by m plus 1 became the other one.
You were wondering how, and then I didn't hear.
So the last simplification, I just didn't get it. Like
Okay.
So
2m divided by m plus 1.
okay, you're just adding and subtracting. Okay.
Yes, I just write a 2m. I want to get 2 out.
Mhm.
So I write 2, instead of 2m, I write twice the denominator, twice m plus 1, and then I just need to subtract 2 in order to have the same. So this you agree with, right? With this the first equality.
Yes, yes.
And then I just tell that, okay, then it means that first that is there, 2, minus 2 divided by m plus 1. Do you understand now?
Yes.
Okay. Any more questions?
No.
Then let's move on. Let's see what we solve now. It's nice exercise, but let's leave it for now. Yet another exercise. Let's leave it for now. Okay, that's actually maybe something we can do quickly. So exercise 5. So the problem 5, exercise 26, 20.6. So let's solve that. Suppose we are given an instance of the load balancing game with m identical machines and n tasks whose weight are bounded from above. So each task weighs at most, not at most, yes, at most alpha of the optimum. For some alpha between 0 and 1. Identical machines, and each task weighs at most. It then shows that the cost of a pure assignment cannot be more than 1 plus alpha times the optimum for any equilibrium. Well, that's not so hard, I think, but not. It's a nice exercise. So, do you have any idea, like the general idea, how to approach that?
Mm. Can we modify the above expression that 2 minus 2 divided by 1 m plus 1, that one somehow?
You want to modify it so that you get 1 plus alpha from alpha. Is that what you mean? Or I guess I did not heard you completely, and therefore I'm not. Which expression do you want to modify?
We have this expression, right? Cost of any assignment is equal to 2 minus the one we just.
Okay, so you want to modify that given what we know. So the cost is at most that. Now, unfortunately, it seems like, how can we use that alpha? So we know that each task costs at most alpha of the optimum. How can we prove therefore that the cost of the equilibrium is at most that?
Oh,
Maybe we can go into the proof and see how the proof itself of the theorem, which we did on the lecture, maybe that can make some use of this additional assumption, maybe, but we can actually do it simpler.
okay.
But if your idea was to modify this formula, I don't see how we can do it. No, I don't see how we can do it. But we know that basically the idea which I had, that it's an equilibrium. So what we want to show is that if the optimum, if the cost of an equilibrium were larger than this, then we need to show that it's not an equilibrium. And we do that using the fact that there are small tasks, that all the tasks are small actually. That's the idea I had. So, okay, let's start writing. And then see. So 5, except for the 5, 4, 2. So, what we see is that let A be an equilibrium assignment. Now, assume to the contrary that it's not the case, what we want. And from that assumption, we are going now to prove some contradiction that we can deviate. So, assume to the contrary, or assume by contradiction, that the cost of this A is strictly A at least. So basically, assume that that is contradictory. It is at least 1 plus alpha of the optimum. What does it mean, first of all? There should be then at least one task, at least one machine, which has this by definition. So there exists some machine. We have rho and q, right? Let's use it. There exists some rho, some machine rho in one element, such that the load of rho is at least 1 plus alpha times optimum. But then there has to be also some other machine, Q, such that the load of that machine is at most 1 minus alpha times optimum, simply because the average is at most optimum. So if one machine is going that direction, there has to be something which is small. Do you understand?
No, because we don't have a bound on the number of tasks, right?
We don't, and I don't use anything. So let's see. Okay. We assume that the cost is at least 1 plus alpha times optimum.
Yes.
Assume by contradiction.
Yes.
Then it means by definition that there is a machine. It's all pure. There is a machine such that the load on that machine after or under A is at least 1 times alpha, 1 plus alpha times optimum, right?
Yes.
Okay. Now, what does it mean that there is an optimum? That if you could kind of smear the machines equally, it would be at most optimum. So if there is a machine which has at least 1 plus alpha times optimum, then there has to be a machine that has at most 1 plus alpha times optimum, because the average has to be at most optimum.
Okay. Yeah.
I can write it exactly like with the sums and all, but you understand it.
Yes.
I can write. Okay. Thank you. So thank you for the question. Now let's move on. Now we need to find a possible deviation. So what does it mean that we have this? So any task I such that AI goes to machine raw would strictly benefit, that's the claim, from deviating, from moving to, in a way, from deviating from what we did before, in other words, from moving to machine Q. Because in machine rho, at rho, the other tasks weigh at least optimum, because alpha weighs at least at most, actually even more. Alpha weighs, yes, at most alpha optimum. That's the assumption. So at machine rho, the other tasks weigh at least optimum. And the load of machine Q, so there, the other task weigh at most 1 minus alpha optimum, and alpha is greater than 0. So there is a strict gain. Do you agree?
Yes.
And that's of course contradictory. That's a contradiction to the assumption that it's that's a contradiction. A contradiction to the assumption that A is an adjective. So we are done. Any questions?
No.
No. The second question, actually, there is a typo in the question. They want us to show that the cost is at most O of optimum under some assumption alpha, and then they write for any profile P. I don't know whether actually it's true for any profile. Let's show for any pure profile alpha. Maybe we can also show for some general profile P. Maybe that's just a typo. I don't know what they meant. Let's just show that for alpha. So assuming alpha, I mean for A, excuse me, for pure A. Assuming alpha is 1 over log n. How can we show this? First of all, what do we know from the first part?
No, I'm not able to connect.
I don't hear you.
I'm not able to draw a connection.
Okay, first of all, the first part does give us some bound, right?
Yes.
We already know something immediately. Don't you see? The first part tells us from part A, the cost of A is at most, it's strictly smaller than 1 plus alpha times optimum. That's something we proved in part A, right?
But that is under these assumptions, right?
Under which assumption?
That the weights are bounded.
Yeah, but these assumptions are given for the whole exercise.
Okay, whole. Okay, yes. Okay, yes. Then yes, of course. Yeah, I totally missed that. Yeah.
Before A. They're in here.
Yeah. So yeah, I missed that. Yeah.
So okay, no problem. So we know then by part A, cos A is at most 1 plus alpha times optimum, which is, now we substitute the alpha, 1 plus 1 over log m times optimum. And well, I think that's already right. That's immediate that it's because 1 over log m is some constant. It goes to 0, so it's bounded by a constant.
Oh, yeah.
M, of course, has to be at least greater than 1, otherwise it would not be even defined. So we assume that they assume that m is greater than 1 by writing this expression. And then log is at least the log of 2, not just greater than 1. Is at least 2. That's the assumption, actually. So m is at least 2, therefore log m is at least log 2. Doesn't matter what it is. And therefore 1 plus 1 log m is at most some constant. Well, it's at most 1 plus 1 log 2. That's some number. And that's therefore this thing is O. I mean, symptotic notation of optimum. That's what we need to prove. Do you agree?
Yep.
Okay. Next. Okay. Now we go to the scheduling part, not scheduling, the resource allocation. Let's go with a simple question that which I meant to help us understand that, refine the understanding. So I remind you the system, and let's go to the book because it's nice if you can see the book, not only the lectures but also the book. I remind you the system. You don't have to read the book. I just tell, so when I tell you I remind you, I don't mean that you should have read the book. So of course you're welcome to read it. But I just remind you the system, which was basically, forget any game, just the allocation problem. You want to allocate something of size capital C. So you give non-negative shares to R players of size capital C. They're not in players now, just to R whatever. And the total utility you want to maximize. The utility is that. Do you remember that I call this VR? The values I called V. U is the utility, which is the values minus what you pay. But so I call this, I wrote this differently. But besides that, that's like here. Do you recognize the system? Or do you want me to explain a bit more?
No, yeah. So basically, it's something like a optimization problem, right? Maximize utility.
Yes, exactly. That's just the optimization problem. Assuming that you know everything, the utility function, just you maximize the utility. So write this system for those functions, linear functions. We'll just write this down. Let's write it down. What is the system? Well, for those functions, for VR, the value function for the given amount of dr, R is just one of the players, is simply some alpha or A, let's say A, times dr. So the system for that is the following. Maximize sum of that 1 to the number of players, AR, DR, right? Subject to what are the conditions?
The sum of dr is less than
right? The sum of them is at most some c, and each one, of course, is non-negative. So these are the conditions. Not reals, it's just R, number R. Don't confuse R with reals. I hope you don't confuse it. Let me just maybe write a bit more clearly. Good. The next question is, does it always have a unique solution? So I reminded that you said that if these functions, and there is this in the book, if the functions v, the utility functions, are strictly concave, then the optimum solution is unique. But we don't even go. That's kind of the thing of this calculus, that if the functions those are strictly concave, then the optimum solution is unique. It always exists because this is an optimization of a continuous function on a compact domain. But the uniqueness is if they're strictly concave, then they're unique. What happens? But is it maybe there is? It's actually maybe always unique, or maybe not. So is it always unique? If not, give an example. If yes, prove. I remind you that the functions we use here, the utility we are used here, are not strictly concave. They are linear, so they are both concave and convex, but they are not strictly concave or convex. They are not. You remember the intuitive definition of strict concavity and convexity is that. So this, for example, would be okay. It's strictly convex. That for any such segment between 2 points, everything which is strictly between those points has to be strictly between that segment. That's strictly. I can write it down formally, but that's strictly convex, and that's strictly concave. 22 points. The graphic of this above. That's strictly concave. Of course, if the graph is linear, then it's not strictly. It's exactly there. It coincides with all those tangents. So our functions, our VRs are not non-strictly concave. So we can't use that claim from the lecture. But what we can maybe then do is to prove that there is still a unique solution, or we can maybe show an example where it's not unique. So what do you say? Actually, what do you say?
Mm. This
Let's go back. Let's go maybe back to the what we have written. So I want to prove there is a unique solution, or to show an example where it's not unique. And the assumption is all those functions are linear. So, okay, I give you a hint. The solution does not have to be unique. So just prove it's not unique. Just give a proof it's not unique. Or give an example where it's not unique. If you don't care, actually, think about something like really simple. What if all those functions are the same? What if all those functions are the same? Will that then matter it all for the objective value, how we divide this capacity?
No.
That's a good example. Actually, the solution isn't unique, isn't all. For example, if a the coefficients of those functions are the same, so a1 is equal to a2 and so on until ar, then any feasible solution, or any not feasible, any solution, because feasible solution may not fully utilize D. Any solution not fully utilize C. Any solution with any solution, any feasible solution, such that the sum is fully utilizes C, is optimum. I can even like prove it if you want. Basically, because the sum, the objective function is sum of AR dr. Now, if those A are the same, so call it some A, just A. Then we can just say that it's just A, the same number, which we can pull out of the sum. A times the sum. And so if we just need to maximize the sum, and that's so as long as the sum is optimum, that's going to be the same. Do you understand?
Yes.
Okay. So do you have some energy like for one more exercise?
Yeah.
Let's solve exercise 7 because we had this delay because of this technical problem. So price finding, that's something simply a technical thing to see that we know how to do it. So compute the prices and the allocations for the following cases, assuming the proportional allocation mechanism. Let me just remind you what happened. I use this to show you what the book does, this kind of opportunity. So basically the book says the following. In the proportional allocation mechanism, you demand that the total allocation is going to be C. What is the total allocation? The sum of what you get. What you get is your bid divided by the price. And then the price is the total sum of the bids divided by C. That's how the price is determined, such that you will have this allocation, the sum of allocations BC. That's how the price is determined. And then the allocations are determined either by W, you get just WR, what you bid divided by the price, or can also be shown that what you get is always the share, the relative share. Well, let me show it. Let me just write it down. Uh, 07. So the approach, how do we solve it? So first, the sum of WR divided by the price, WR divided by the price, somehow it's mu, is equal to the C. Basically, that is if and only if mu is equal to the sum of WRs for the bits divided by C. And once we've done that, the allocations, we want not only to find the price, but also to determine the allocation, the actual allocations are dr, which is what you bid, how much you want to spend, divided by that price, which you've just found. Or you can just write it further. That's one approach to find it. Or further, basically what you bid divided by that formula, and substitute this formula, and then we will have the sum of the prices of the bits of the others. Okay, I've written it in a very unclear manner. Let me just write it. It's not dr. Okay, I can just use R and S. I can just use another index. It's dr. And then so WR divided by mu. Mu is the sum of W divided by C. Since we have already R, and let's call those WS's. That's they are the S from 1 till R. And C now goes up. C. So that's still the proportional allocation. That's also the way, that's also something we solved before. So we can choose to find the allocation. We don't have to go through finding the price again. So is the method clear?
Yes.
Okay. Now we solve. Now that's simply solved. So 1. Okay, now I have a problem. It doesn't want to run. Don't know why, but it doesn't want to write. Let me try. It seems to be it seems to be not working. So now it's not shifted, it seems to be not working at all. It does not see it. Okay. Okay. Let's try once more. Disconnect and then connect work. So 1. C equals to 1, W1 is 1, W2 is 2. Then the price is the sum of the W's, so 1 plus 2, divided by C. So it's 3. And the D, that the first player gets, is what she beats, 1 divided by 3. What the second player gets is what she beats, 2 divided by 3. Or another thing, alternatively, let's first calculate the first example in two ways. Alternatively, D1 is equal to the ratio the ratio of W1 to the sum of the W's times C, which is again 1 over 3. And D2 is equal to W2 times the ratio divided by the sum of the W's times C, which is 2 or 3. Okay, let's continue. So 2. So now C is 10 and W's are 1 and 2. Now let's solve only by one approach. So the price is equal to the sum of the W's divided by the C. So it's 1 plus 2 divided by 10. And now D1 is equal to the, let's use the price, for example. So the price divided by, actually, the bid divided by the price. What's the bid? The bid is 1 divided by the prices. So the price is 0.3. D1 is that. And D2, let's use the other method, the relative bits. So what are the relative bits? The relative bits are 2 divided by 1 plus 2 times C. Whatever it is, it's 2 dot times 10. So it's 20 divided by 3, which is 6 and 2 thirds. Doesn't matter. It's enough. 3. Okay, let's solve this till 3, and then the rest maybe I'll do it as a homework. So C1, C is 1, W1 is 1, W2 is 2, and W3 is 2. What's that? What's the price now? The sum of the W's divided by C.
5.
So, yes?
5.
Yeah, 1 plus 2 plus 2, so it's 5 divided by 1. Exactly. 5. D1 is equal to the W of the first one divided by the price. D2 is equal to the W of the second one divided by the price. And D3 is equal to the W of the third one divided by the price. Using that formula. Okay. Let's call it a day. I think we've covered quite a lot. So have you got any questions?
No, I assume there is one more homework, right?
Yes, yes.
Okay.
I am planning to give you one last homework. Okay. So since you do record this today, please give me send me the link for the
Yes.
record. Okay, thank you.
Thank you. Have a nice
Have a
weekend.
good weekend. Bye.